Hi, this is Nirmala Rednam. In this video, we are going to discuss exercise 6.1 and 6.2. So, let's look at the first question. They're asking us which of the following numbers are not perfect cubes. So, we have already seen the method to check whether which of the, if the given number is a perfect cube or not. What we are going to do is we will be doing prime factorization in order to check. Okay. So the first number given here actually is pretty obvious. 6 cube is 216. So yes, it is a perfect cube because 6 cube is 216. So if you remember in the earlier video, I told you that we can, kind of reduce the steps we do in our prime factorization by taking the numbers other than the prime numbers. So usually what we do is we take the prime numbers 2, 3, 5, 7 and 11, so on, right? That is what we have been doing traditionally. Now what I am saying is whenever you have numbers which are product of two distinct prime, for example 2 into 3 6 or 2 into 5 10 or 2 into 7 14 or 3 into 5 15 or 3 into 7 21, so on. I am going to go ahead. Now this is a very small 3-digit number, no problem here even if you start with 2. But when you go to other sums that they have given which have like 4 digits, 5 digits and greater than that, you will see that this is going to really save a lot of your time. And the reason it is going to work is because it is a product of two distinct prime numbers. Okay. So it is a product of two distinct prime numbers, and so we will not be missing out on any grouping that we would have been if, for example, I have a number which, in prime factorization, if I had written it like this and concluded that it's not a perfect cube. Now this is wrong, right? I can't conclude that this is not a perfect, this in fact is a perfect cube. Where did the mistake happen? The mistake is that I considered 8 as a factor, which again is nothing but 2 into 2 into 2, which is in fact a group of 3, right? Now these things will not be, nothing will be hidden inside this 6 because it does not have two twos or a couple of twos or a couple of threes. It has two distinct prime numbers. So that is the reason why I'm saying that if you understand this, then you can proceed in this way, right? So I'm taking 6 directly because like I said 6 is 2 into 3, correct? And so I am going to have 6 cube. So 216 is nothing but 6 cube. So it is a perfect cube. Now let's look at the second question. 128. So 128, if I want to look at the larger numbers, none of them is going to work. Even 6 is not going to work. So I am going to go back to my original, 2. Let's start with 2. So quickly let's do this. We have got 8 is 2 cube. I have, this is one set and this is one more set. I'll write 2 cube into 2 cube and I have 1 2 left. So this is not a perfect cube, right? So this is not a perfect cube. Next question, they're asking 1000. Now clearly now 10, like I said, is 2 into 5, two distinct prime numbers. Therefore, I can write it as 10 cube and not worry about having missed some of the factors hidden inside them. And I am able to group it as a group of 3. Therefore, it is a prime, it is a cube, perfect cube. Next is 100. Like I said, without the fact, you can do the factorization and check it, but if you're understanding what I'm saying, you need not do this. Okay, what I'm saying is I have 10 here in the secondary numbers that I'm talking about. I have this as 10 square, so I can be sure that there is no hidden factors here which can be grouped into group of 3, right? Because 10 is a product of two distinct primes. So this is not a perfect cube. Next is 46656. Okay, now here you will see the merit of what we have been talking about. Now this is a 5-digit number, pretty huge number, and if I were to start with 2, right, it is going to take a lot of steps. It is going to be it's going to take a lot of space, lot of time, lot of steps, and instead, let me check if 6 is a factor. If you 42 and again 42, 42 and then 36. So 6 is a factor. I can use 6 because it's a product of two distinct prime numbers. I'm going to use 6. Okay. So 6 sevens is 42. Again sevens is 42. And one more time I have sevens. I have 42. And then I have 36 here, which is 6, 6. Okay. Now I'll proceed with 6. 6 ones, 6 twos, 57. So I have 6 eights 48 and 6 nines 54, and then I have 6. So you can see how quickly we are bringing down the number very quickly, right? 6 twos, 6 ones, and this is 6 cube. This we already know is 6 cube, right? So I'm going to write this as 6 cube into 6 cube, which is a perfect cube. As opposed to if you were to start with the 2, right, then you would have ended up with 2 into 3 here, and one more 2 into 3, so you would have ended up with 12 steps, correct? So you would have ended with 12 steps of factorization, which can be avoided, right? So we are saving a lot of time here. This is your 5th question. So let's look at the second question. They're saying find the smallest number by which each of the following numbers must be multiplied to obtain a perfect cube. So clearly the given number is not a perfect cube, and here we need to factorize and see which are left out after grouping them into groups of 3, and then decide the number that it has to be multiplied with. So let's look at the first number given to us here, 243. 243, 3 is going to work. 27, 27 is 3 cube, right? So I'm going to write it as 3 into 3 into 3 into 3 into 3. This is already a pair. I need one more 3 here, so I have to multiply it with the 3. So that is my answer. Next is 256. 256. So here I'm going to start with 2, 128, 64. 64 is 4 cube, right? So I have 2 into 2 into 4 cube. So here I have a 2 missing. Therefore, I have to multiply it with 2. Now here you can see that as long as I have a cube already, I'm going to keep it aside. I need not continue this factorization, if you know what I mean. And you need to understand this before applying this logic, because otherwise you might end up making a mistake. So this is the actual prime factorization, right? I am saying at this point, because I already know it is 4 cube, the grouping has already been done for me, right? So that is the logic I am asking you to understand. Here I have the third question, 72. Okay, 72 is, now here you can see that 6 clearly is, you have a 6 here, and let us start with 2. 36, 18. When it's a small number, let's not try to complicate matters. So this is multiplied with 3, you will get the answer. 675. 5, as soon as I see a 5 in the ones digit, I have to first divide and be done with that 5. 27. Now this is, like I said, 3 cube, so you can directly write it 5 into 5 into 3 cube. right? So what I need is another 5. So multiply it with the 5 and you're done. Fifth question is 100. Now 100 is 10 square, right? Now 10 is that secondary, the number that I said, it's 2 into 5. So, or you can break it down from here. You can say this is 2 into 2 into 5 into 5. That means I need 1 2 and I need 1 5. Therefore, multiply with 10 and you have your answer. You have to multiply it by 10 to make it a perfect cube. Now let's look at the third question. Find the smallest number by which each of the following must be divided. So in this case as well, what we are going to do first is we are going to first do the prime factorization, right? And then we are going to decide what is the number that it has to be divided with. So let's write down the third question. The first sum they gave is 81, right? 81, if you do the prime factorization, you're going to get 27, which is 3 cube. So 3 cube into 3 is, and this is the problematic part. So divided by 3 and you will get a perfect cube. 128, we have already done 128 factorization. Okay. 32 and 16. Actually, you can stop at 64 itself, right? So I have 7 2s. You can stop at 64 because it's 4 cube. 4 cube is a perfect cube into 2. So divide by 2 and I'm done. I will have my perfect cube, which is 4 cube. Next number that they have given is 135. 5, I have 27 and this is nothing but 3 cube. So this number is 3 cube into 5. So divided by 5 and I have my answer. So in the exam, ideally, if when you have this question, you have to do the prime factorization using all the prime factors and get the final, write it as a product of prime. All these partial marking and all these steps will carry marks for you, right? So you need to do that. But what I'm saying is, in order to quickly check it and in order to, save time while practicing, you can simply skip that part. So I have 192. I'll go for 2 now. Okay, so this will give me 96, right? 96, and then I have 48, 24, 12, 6 and 3, right? So I have 2 sets of 2's and a 3 finally. So I have to divide it by 3 in order to get a perfect cube. Next sum is 704. So here I have 352, 176, 88, 44, 22, 11. So I have 2 sets of 2's, 2 cube and 11. So divide by 11 and you have your answer, right? So this is your third question. Next, fourth question. Parikshit makes a cuboid of plasticine of sides 5 centimeter, 2 centimeter and 5 centimeter. How many such cuboids will he need in order to form a cube? Now here, what do we mean by a cuboid? It is a 3D solid shape with length, breadth and height, which need not be the same, which need not be equal to each other, right? Now, how many such 5 by 2 by 5 cuboids does he need in order to form a cube? So, what we are going to do here is, first of all, find out the volume of this cuboid, right? What is the volume? LBH, right? I have to multiply these three and I'm going to get 50, right? So the volume of this cuboid is 50 centimeter cube, right? So this is the volume of the cuboid. Now what they're asking us is simply what should be multiplied to this in order to make it a perfect cube. So you can see here we already have the factorization. So I need two 2's and I need one 1. So what is this? 20. That means that I need 20 such cuboids in order to make a cube, because then I will have the product as 1000, which is a perfect cube, right? But let's also try to visualize it, because they have given us a cuboid. Now that I know it's 10 cube, I want to make length, breadth, right, and height. All the three should be equal to 10 centimeters, right? So I'm going to try and draw this. So this is the final cube that we have, right? So how did they place the cuboids? One arrangement I can think of is, if you have, this is 10, right? I have 5 by 5 by 2. So maybe this is the 1 5 and half here. This is another 5 and this is 2. So maybe this is, you can place one, cuboid in this manner, correct? Can you see this? So this is one cuboid. Now in this way, the base will be covered by 4 such cuboids. So this is one, you'll have one more here, you have the third one here, and you'll have the fourth one here, right? And then that is one layer. The height of that layer is 2 centimeters, and this entire height is 10 centimeters. That means that such layers, you have 5 such layers, right? So 1 2 3 4 5, 5 such layers will give you uh, you know height as 10 centimeters. That means 4 into 5 is 20. So you can see that, you can try to visualize how we got these, how we can arrange these cuboids in order to get the cube of side 10 centimeters. So let's move on to the next exercise, where we'll be finding cube roots. The example sums you can go through. You have one thing, discuss and write here. State true or false for any integer m square is less than m cube. Okay, first of all, is it true? Is m square, you know that m square is you know uh, m into m. M square means m into m, right? So here I have m square is nothing but m into m, and m cube is nothing but m into m into m. So clearly you have three numbers here, so this must be greater. Is that true? No, it is false. Okay, this statement is false because they're saying any integer. They're not saying positive integer, they're saying any integer. And if that integer happens to be negative, okay, this will turn out to be a positive number and this will turn out to be a negative number, which means that m square in that case is going to be greater than m cube. Okay, so it depends on the sign of m. If had they said positive integer, then this statement would have been true. But they did not mention positive, therefore you have to say it is false. And you can give a counter example. Minus 2. Minus 2 into minus 2, m square is nothing but plus 4, which is greater than minus 2 into minus 2 into minus 2, which is minus 8. Correct? So that is your counter example. Now let's look at the exercise. Find the cube root of each of the following numbers by prime factorization. So here, like I said, 64 is pretty obvious. 64 is 4 cube, therefore the cube root is going to be 4. Okay, so 64 cube root is 4. Next 512, like I said, it should be noted to you, it is 8 cube, therefore the cube root is 8. Right? So let's start from 10648. So here, exercise 6.2, I have second, first question, third bit, 10648. So here let's do the prime factorization in order to find out the cube root. Okay, clearly 2 is going to work. So I have 5324, 2662, 1331. This is 11 cube. 1331 is 11 cube. Okay, so this is nothing but 2 cube into 11 cube. That means cube root of 10648 is equal to 2 into 11, which is nothing but 22. Right? Fourth question is 27,000. Now I have zeros. I am going to write it as 10 cube immediately. Okay, 3 zeros means 10 cube, and 27 is 3 cube. Therefore, cube root is nothing but 30. Okay, so I did not do any prime factorization here. 15625. So because I have a 5, I will go with 5, and you can actually check 25 as well, because then you can break it down. 25 is not product of two different numbers, I agree, but you can break it down later in order to save time, is all I'm saying. So 3125, 625, 125. Now I can write it as 5. 25 is nothing but 5 cube, right? So 5 cube into 5 cube. Therefore, cube root of 15625 is equal to 5 into 5, which is 25. So that is my fifth question. Next I have sixth one is 13824. Okay, 13824. Now here you can see that it is a very big number, right? 13824 is a pretty big number, and if I start with 2, it is going to take a lot of time. What I'm suggesting is, let us check 6. Okay, if 6 works, let's see how it goes. 6 2 6 3s and 6 is going to work. Let us see how the calculation is going to be with 6. Okay, 2304. One more time, can I add 6? 50, 48, 20. Yes. So I have 384. One more time I can have 6. 6 6 and 6 4s. Now 64 is 4 cube. Okay. What I want you to do is, see how easily we got the answer. Of course, in the exam you might have to show the prime factorization in the textbook manner, but you can always verify it in a short method like this. Okay, so the next one is also a big number, 110592. That is a big number. So if I continue with the, if I start with 2 again, it is going to be very lengthy, right? So you can check 6. Okay, 6 is not going to work. You can start with 6, right? And then we will see how it goes. Okay, I have 6 does work. Let me tell you, 6 ones and then 6 eights, 6 fours, 6 threes, 6 twos. Okay, 3 0 7 2 5 1 2. Now 5 12 is nothing but 8 cube. So this is nothing but 6 cube into 8 cube. Therefore cube root is 6 into 8, which is 48. Correct? So the next question is 4 6 6 5 6. Okay. Now again you can either start with 2 traditionally, or 6 is clearly going to work. So I'm going to start with 6. 7 7 7 6. 1 2 9 6. 2 1 6, and 6 cube is 216. So you can see here how easily we got the answer. 36 is my answer. Correct? So this is your 8th question. Next I have 175616. Okay. Now here 2 is clearly going to work, but first let's get the bigger factors if there's anything else. You don't have a 3 here. Let's check 7. 7 twos 14, 7 fives 0, and then I have 56 and one more 56. So 7 is going to work. 25088. Again, when I check 7, I'm going to get 7 3s 21, 7 fives. I have 38, right? 35, sorry, 58. 7 eights is 56, and then 7 fours 28. 7 fives, 1s, 2s, and 5 12 is 8 cube. So I can write this as 7 cube into 8 cube. So cube root of this is, sorry, 7 into 8, which is nothing but 56. So I'm telling you again and again, this is for your reference and to verify in a quick manner. In the exam, when they say prime factorization, since you have not done exponents and powers and you don't know why this is cube root, you need to show all the factors in the prime factorization. But for the purpose of verification, you can quickly check it in this manner. Next, 91125. They want you to realize that, in fact, that is why they have given that thing discussed right there, where they've given, number of a number of zeros as 2, and then ask you what could be the reason that it's not a perfect cube, and so on, right? So because I have a 5, I will proceed with 5, right? And if you want to make it a little, if you want to take a bigger factor, you can go for 25 or something as well here. 5 ones, 5 eights, 2s, 2s, 5s, right? 5 3s, 6 4s, 5s, 5 7s, 2s, 9s, and 729 is 9 cube. So this is nothing but 5 cube into 9 cube. Therefore cube root of 91125 is nothing but 5 into 9, which is 45. Okay, so this is about your first question. And then I have state whether the following are true or false. We'll do that here itself. So the first one, cube of any odd number is even. Is it true? It's not possible, because if it's an odd number, it doesn't have a 2. It doesn't have the prime factor 2, and if I don't have a 2, you will not get an even number in the end. So the statement is false, right? And a perfect cube does not end with two zeros. This is true. We have discussed at length about this. If square of a number ends with 5, then its cube ends with 25. Square of any number, it actually ends with 25. Square of any number ends with 25. We have seen it in the previous chapter. Okay, so this is also not true, and cube could end with either 5 or 25. You can check that. It need not end with 25. It can end with either 5. It can end either with 25 or 75. Right? So this statement is false. There is no perfect cube which ends with 8. That is false because we know 2 cube is 8. Now the cube of 2-digit number may be a 3-digit number. Do you have a 2-digit number, okay, whose cube is a 3-digit number? So let's look at a 2-digit number. So for these kind of questions, what we will do is take the least 2-digit number, which is 10, right? I mean, there's no 2-digit number less than this. This is the smallest 2-digit number. If you take cube of this, you're going to get 1000, which has 4 digits. So this is false. If the least one itself has 4 digits, then any cube after that will have either 4 or more than 4. The cube of 2-digit number may have 7 or more digits. Now, in order to answer this, you have to look at the greatest 2-digit number, which is 99. Okay. If you look at 99 cube, you will be able to answer this question. So, what is 99 cube? So, let us check the value of 99 cube. Okay. 99 into 99 will give you 81, 89, 891. So this is 9801. Now I have to multiply this with 99. Okay. So I have 902, 81 plus 7 is 88. 88209. So if I add this, I'm going to get 992079. So this is a 6-digit number. So they're saying 7 or more, that is false. It's a 6-digit number. So this statement is false. Next I have the cube of a single digit number may be a single digit number. 1 cube is 1, right? Single digit number cube is single digit. So this is true. So the sums like 99 cube, you will be able to do it in a much faster and elegant way once you have algebraic expressions and the identities, where you can use a cube, a minus b whole cube, and things like that. So with this, we come to the end of chapter 6, cubes and cube roots. And in the next video, we will be starting chapter